We're going to talk today about link prediction problem. In fact, both lectures today are on the sort of boundary in between network science and machine learning. Now, did you guys have a class? I'm sure you had a course on machine learning, right? Supervised learning, unsupervised learning, semi-supervised learning. You familiar with that? Yes. Okay. The quality of classification. How to verify the quality of a classifier? Just speak up because I can hardly hear you.
Accuracy, for example.
Okay. Roca-Oak score. Yeah, precision recall curves. Okay, good. All right. Well, then, it's going to be a pretty short lecture, so I don't need to go through all those details. The idea is very simple overall, right? So you have a graph, and you would like to be able to predict links, right? And you can formulate it in various ways, this problem, and we're going to talk a little bit about the ways to do it. The magics you can use and how you can formulate this as a supervised learning problem. Well, and then how to solve it. So, there are several problems you can solve with this link prediction approach, right? So the very first one is, of course, you do have evolving network, right? And you would like to see where within the network you will get, your next link, or whenever, if you, for example, select certain window, right, time window, see within that time frame, how many links and where they appear in the network, right? Very, very, very simple and straightforward in terms of understanding it. How can we use this? Well, again, on one hand, it is network evolution. On the other hand, you can use this, of course, also as a recommendation system. And in fact, it is used a lot. This type of approach used a lot, say, in Facebook, right? If you go there and it says, oh, hey, this is the people you might know, right? This is actually a recommendation system. It actually says there is links here that you do not have in your network, but you might consider having them, right? So, and Facebook uses one of quite simple versions of the prediction algorithm, but there are multiple levels there of complexity you can put on. You can also think about this as, of course, if you have a bipartite graph or a graph of where there are two types of nodes, you can also think about this as a recommender system. Let's say one type of nodes will be resumes, right, job seekers. Other type of nodes will be jobs, right? And so the question is, okay, for which job you should apply, and that's also can be solved based on the same approach, right? Because you have, say, graph, which will be the jobs you had, right? So the matching of your resume to the jobs, and here is, other alternatives, other links you could potentially form. Or if you think about, say, collaboration graphs, collaboration networks, the simplest version would be co-authorship network. You write papers with some other people, right? So you co-author with them. So again, here you can think about graph of, for example, people and research papers. And again, it can recommend you who to select as a co-author for your next paper. Okay? So there are multiple sort of problems you can formulate in terms of link prediction. Now, there are other things you can actually, there are some more of technical uses for this, is to see when you get some data set, is to see if it is consistent, right? So look for anomalies in the data set. Anomalies could be in terms of missing links, or anomalies could be in terms of links existing somewhere where you wouldn't expect them, right? So you look for overall patterns, and you realize that certain type of links shouldn't be there. And so you can verify data, look for anomalies look for inconsistencies. For example, that type of approach is very powerful if you do fraud detection, right? So when you look at financial transactions, nodes are financial institutions or accounts, links are transaction, money wiring, money transfer. You can actually see the patterns in there, and you can see where sort of certain things pops up that you wouldn't expect them to be there based on overall structure. And also, data in real life often quite noisy, and so certain links can be missing. It's not because they miss in the real world, right? But it's because the way when you collected the data, you didn't collect that, or they might exist because again of the noise. So the interesting thing with networks versus sort of any other data, right? In any other data, you might say, okay, well, look, here's the value, right? And there is a noise, it's corrupted by noise. Let's say that the real value is, 0.5, but because of the noise, it's 0.51, right? Or 0.49, whatever. Here, it's actually, there is a link or no link, right? So it's somewhat binary. And if you have a noise here, a little bit of a noise in the data, it means that it actually creates spurious links where they shouldn't exist, right? So it's a little bit more of kind of black and white story. What you can predict? Well, most of the time, we predict link existence. You can also, of course, again, setting up a supervised learning problem, you can think about, link type. You can set this up also as a supervised learning plus a little bit of regression, and you can predict link weight. So, pretty much any flavor. Now, since you do know machine learning and you worked on this type of problems, why do you think? Okay, I'll tell you. I'll just postulate this. This is a quite challenging machine learning problem. Now, why do you think it can be challenging? Or maybe not. Maybe you don't think it's challenging. So what makes it slightly different from your typical machine learning exercise?
Because the structure is enough. We don't have real values, for example. We don't have features like in other machine learning problems.
So first of all, yes, I agree. What happens is you kind of your labels and features, they're sort of intermixed, right? Because you might think of edges on one hand, the existence of edges, that's your labels, right? If there is an edge between two nodes. On the other hand, they actually create the structure of the graph. So they need to be used also somehow within the features. And so yes, that's technical challenge. You have to be very careful with this, right? But what else? What's sort of conceptually challenging here? Think about overall sort of space of possibilities, and how balanced are your classes. Remember, the easy problem in machine learning is when your positive and negative classes are what? Balanced, right? When you have approximately the same number of positive examples and negative examples, right? And so, which means the distribution is quite even, right? And if it is not, you have to deal with it. And if it is a little bit different, it's okay. Now, if there is difference in orders of magnitude, that makes the problem much more challenging to solve. Now, in here, that's actually one of the biggest problems, right? If you think about this, when you have a dense graph, right? When you have a complete graph, all edges are present, right? So then it's going to be, the possible number of edges is, n times n minus 1 over 2, right? So approximately n squared. In real graphs, those we work with, there are much fewer edges, right? In fact, we're dealing with sparse graph most of the time with very low density. So there is just much less edges than n squared. So which means number of missing edges is huge. So the huge number of possibilities where you can predict an edge. And so that creates two things. On one hand, first of all, when you create your data set, you have to be careful how to select positive and negative examples, because overall, of course, there is sort of many more negatives or empty spaces exist. Plus, the biggest challenge is you actually need to go and literally, if you want to predict within the entire universe of possibilities, you actually need to go through almost n squared pairs, and for each of them, think if there's going to be an edge or not, right? So you need to do something smarter than that, because again, with large graphs, n squared is not an option. And so it's very easy to make a mistake here, right? So that's what makes it challenging. So there are two factors. First of all, this notion of sparsity of the graphs and the fact that you have very, very unbalanced data sets. And second, that yes, you have kind of mixed, the labels and the features are kind of getting mixed up because of the structure of the graph. But let's see how we can resolve this. So first of all, based on what we learned in the previous module, right? And let's think about just social network. Can you give me some, feature or sort of some suggestion, some very simple approach that can tell me or can suggest that there is a high chance that there is going to be a link in between those two nodes than in between some other two nodes. Let's say I want to just rank all the pairs by the likelihood of a link being formed between them, right? So any graph property that comes to mind that can help me with this, right? Just something very simple. Degrees. Actually, degrees, we're going to use that too. That's true. But the most obvious, the sort of the most straightforward. Remember when we start talking about this whole social network stories, there was a sort of three major properties I kept telling you, right? What was those properties? Power law degree distribution. What else? Yeah, 6 degrees separation of small world, and the third one was the existence of a lot of triangles, right? The fact that, two of your friends most likely know each other, right? So if you have two friends, they most likely know each other. So the fact that there is a triangle. So sort of working backwards, if I have two nodes, what will increase the likelihood that they're connected in the social network? If they share a friend. Now, if they share 10 friends, that's actually a strong signal. If they share 200 friends, you're actually becoming suspicious, right? So, and by the way, again, I know you're not a big users anymore of Facebook, right? And I'm not sure in Telegram if there is such a feature, right? But in Facebook, it tells you that, oh, well, you have that many friends in common with somebody, right? Contacti also. Is it still around?
Yeah.
Okay. I thought they got acquired and then they're still around. Okay.
We had a project which Ilya Andreevich gave us to get the data from UK.
And you still can get it?
Yeah.
Oh, wow. I mean, I know, well, we started those things like probably 5 years ago, 7 years ago, and that back then it was very easy to get data. But, after all this, stories with data leaks, et cetera, and security, they clamped down on this, and so you could not get any more data, but good that you could. All right, anyway, so yeah, it actually tells you, hey, there is that many people in common, right? And that gives you a suggestion, gives you an idea that, for example, you might know this person, right? So here is you, here is the person, and they tell you, oh, you have 20 friends in common. You're like, oh, wait a minute, who the heck is this, guy if we have 20 people in common? Right? And so that's sort of very powerful suggestion for you to actually make a friend, right? Or if you think also, hey, you and this guy have 10 co-authors that you share, right? So you worked with 10 people, he worked with those people and you worked with those people writing papers. Well, you probably need to meet this guy, right? Because he probably works in the same domain or in the same field. So that is a very powerful feature, right? But there might be many more features. So the easiest algorithm, and in fact, that's sort of the first algorithm that was proposed, was, very simple. You literally, go through all the pairs, all the possible pairs. Yes, there are n squared. Let's say we're not dealing with huge graphs. We'll just sort of slowly go through them and score each pair by the likelihood that it might form a link, right? There might be a link between it. And, sort the pairs by decreasing score, set up some threshold and say, okay, well, this top n pairs or top 10% or whatever, that's our candidates for forming pairs, right? And the score can be, as simple as you described. Okay? Okay, I mean, that works. Not perfect, but, you can make this work. But if you think about this a little bit more, what about other scores, right? You can probably come up with other features. So what other features could you come up with in terms of those that can tell you, that can give you a hint that there might be a link, or they can sort of force the link to happen? Like you just mentioned degrees of the nodes. Why do you think degree can be a feature? And by the way, notice, so we're talking about a link, an edge, right? So it means we need to talk not only about degree of one node, but probably...
I meant that if two nodes have very big degrees...
Okay. For example, you add... Yeah, for example, you can add up the degrees or multiply degrees, and it's high number. Now, why do you think that feature can actually tell you or increase the probability that they are connected?
So that in some maths you have a
Mm-hmm.
So when nodes with high degrees are connected to each other, are more likely to connect to each other. So this kind of networks might be the case.
Good idea. Actually, well, in fact, there are properties, right? Associativity, disassociativity, right? And it's not only about high degree nodes. What you're talking a little bit more is to express it more precisely, is going to be, for example, nodes with high degree connects with nodes with high degree, right? Nodes with low degree will connect with nodes of low degree. That's on one hand. On the other hand, we also previously discussed, remember we talked about preferential attachment models, right? The Barabasha-Albert model, right? This is a model of the network, and we assume, some of the networks actually evolve that way. Within that model, the probability of connection to a node is proportional to its degree, right? And so in this sense, yes, like, heavy nodes, probably, they're heavy, heavy in the sense of number of connections. They're probably heavy for some reason, right? And they're either very active in establishing nodes, establishing connections, or whatever the reason is. But, it can be a feature. What else?
Maybe some
Communities. Let's say you have two nodes that belong to the same community, right? That and the community really, again, has happened because there's something in common, whatever, but they're within the same community, so there is a bigger chance that they either already know each other or they will connect. Okay, what else? How about, we talked about, having one friend in common, right? Which is sort of one step away from the node. What about if if I compare two pairs of nodes, there's one pair of nodes, there's another pair of nodes, and this pair of nodes connected through not through one friend, but you need to go through two friends, and this pair of nodes, if you want to get from this guy to this guy, you need to go through 8 steps. Which of those two you think will more likely form a link? Probably the one that has a shorter path, right? So you can think about shorter path in between nodes, right? And et cetera, et cetera, et cetera. So we can actually sit here, brainstorm, and come up with probably hundreds of those features that can be predictive, or maybe not. Now, all right. So now you have all those features, right? When we had one, what did we do? Well, we just sorted by it, right? We sorted by this value. Now we proposed at least 5 more. What do how do we want to deal with this? Sort by one, sort by another, sort by the sum. Yeah. So the easiest way now, these are different features. We need to combine them somehow together, right? Each of them will affect. We hope that we know how they actually, each of them, increase or decrease probability of the forming of the edge, but we don't know for sure. So what do you do? Well, you build a model, right? And the target of this model will be, either you can think binary target, and then it's going to be a classification problem, or you can make it more of, probabilistic target, and you can make it, use like logistic regression or whatever, try to predict the probability itself, right? Make sense? Okay. Well, that pretty much what I just described is like sort of, high, sort of big picture, right? High-flying picture. Okay. So let me just go over, a few of those scoring functions and what we talked about, they usually call it scoring function. The first one is, just number of common neighbors, as we discussed, right? How many close friends. You can also do it like, you can do instead of that, you can just use Jaccard coefficient, which is just this number normalized, right? Then there are a lot of interesting features, and, don't ask me how people came up with them. But there is this sort of, Adamic Adar, and that just says because from the page, that's the first names of the guys who wrote the papers, and they just saw that an important feature will be this one. So it is 1 over logarithm, and this is number of common neighbors, right? So not just number of common neighbors, but 1 over logarithm of the number of common neighbors. Somehow that is becoming a good feature, and you'll see this in a few experiments. Then there is this notion of the shortest path, right? So where you have the shortest path in between the two nodes, right? And if it's shorter, it increases the likelihood. Then there is this cut score. Well, cut score, maybe you remember when we talked about centrality of the networks, of the nodes, there was a Cutts metric of centrality. But the idea is you actually take into account path length, shortest paths of any length, but you combine them together with some weighting parameter, right? So it just tells you like if there is a direct connection, if there is a one friend in common, then this coefficient can be high, and if you go for like 2 steps away, decreases, 3 steps even smaller, 4 steps even smaller, etc. Right? So you can actually do this, and that takes into account all the shortest path in the graph. You can also do like page rank situation, but with the difference that this is called personalized or rooted page rank. This is a page rank that you compute centered at this, for example, node, right? And personalized or rooted page rank means that, remember, in typical page rank, after like random walk, you can actually hop back. Hop to any node within the graph. In personalized version, you just hop back to selected or rooted node. And then there are also various other stories, and this is actually, notice this thing because we're going to use somewhat similar story for the next lecture. But here, what we calculate is what's called hitting time. So this is really a number of steps that takes a random walk to get from one node to another, right? So first of all, if there is no path overall, right, that's going to be like infinite, right? You'll not get there. But then there might be multiple paths usually in between two nodes. And what you do is you calculate random walk. So you start on one node, and it just sort of randomly walks. Eventually, it will go through that other node. And then you calculate on average how many steps it makes. Now, you can do it by using simulation, or you can do it, numerically. There is ways to do it with matrices. Then there is the notion of commute time, which is getting there and coming back, right? And then there is, various sort of normalization, normalized heating, normalized commute time, and PG and PI here is the stationary distribution, the probability of being on a particular node in the network. Say if it is undirected network, this is going to be proportional to the node degree. So So there are multiple metrics like that. This is, again, some sort of basic metrics, but there are a lot of metrics that are based off random walks, right? So you start, you're launching random walk. You either simulate it or you actually compute it. And that what you use as, as a feature to your classifier. And then there is this sim rank. I think we talked about this rank, did we? Yeah, we did. I don't see you remembering it, but we did actually talk about it when we talk about similarity in between nodes. And this is one of the metrics of the similarity, where you say, okay, similarity between two nodes can be computed through the similarity in between the nodes they are connected to, right? So two nodes are similar if the nodes they're connected to are similar, right? And then in this sort of loopy fashion, we can actually calculate overall, we can run this iterations iteratively, and then we can calculate similarity between every nodes. And then you can use this score, because it's pairwise score, also as a scoring function. Now, in fact, if we decided to use machine learning, right, and if we use, some algorithms like, I don't know, like random forest, for example, which is actually very, very robust against overfitting, and it is very robust against sort of extra features. What you can do is you can just literally go and create as many pairwise features as you want and just drop it in there, right? And then it's those that actually work will pop up, right, in the feature importance, and the rest will not hurt you. And in fact, that's why, for example, random forest is sort of the workhorse of all the algorithms, like random forest and gradient boosting decision trees. Those are two algorithms that are pretty much used mostly in the supervised learning prediction problems. Is just because they're so robust, and so even if you add features that don't work, they don't care, right? Versus, say, any regression type of problem where it's going to be a problem if you put in features that are correlated or that kind of acting in the wrong direction. So here, again, the bottom line is, here's a bunch of features that kind of, sort of obvious of the community we're doing. You can, there are actually more. But you can also come up with, any feature you want. The key there, it should, first of all, it should depend, of course, preferably on two nodes, because you're building you could talk about edge, and then it has to be symmetric, because otherwise it's not going to work, right? So that is the feature you talked about, right? Those either product of node degrees, right, or maybe sum of node degrees. Then people use, clustering coefficients, and again, clustering coefficient, if you remember, this is proportional to the number of triangles node belongs to. So if you think that, node is well triangulated, right, so he's kind of in a position where a lot of his friends know each other, well, there is a high chance that he will also know sort of this other node. Finally, there is a very, very different approach. We can talk about it. Actually, let's talk about it for a second here. It goes a little bit to the side from overall machine learning story, but how many of you know about single value decomposition? Yeah. Do you guys remember what it is? Okay. Or principal component analysis, or SVD, right? You just take your matrix and you decompose it into the sequence of lower, loaded, on the sequence of matrices, right? Each of them are low rank, and then you combine them, into that reproduces your original matrix. And so what happens when you do this, if your original matrix has ones and zeros, for example, or has a lot of zeros, when you do load, when you decompose it, if you do decomposition exactly, precisely, right, when you assemble it back, you get your original matrix. But if you use not all the matrices, but say only, some of them, those that correspond to the largest singular values, you'll compose back an approximation to this matrix. Right? But the approximation to this matrix will most likely have, in the places where the original matrix had zeros, it will have some numbers. Right? It's only when you add like the last component that's when it will become the original matrix. And so the idea would be if you think about this as being adjacency matrix of zeros and ones, then it's low degree decomposition that fills in that matrix, or putting non-zeros where there used to be zeros. In some sense, interpreting back, it means it actually predicts your links in those spots. Right? Now, it is kind of, this approach, people do use it, and especially do use it in recommender systems. It's sort of, it's hard to precisely, understand why it works, right? It feels like a hack a little bit, and it is. But it does work, so I wanted just to mention it. We're going to focus a little bit more on this consistent story of actually just creating features. So I think one of the first papers that talked about it, well, now it's like more than 10 years ago, that tried this, and what they did is they actually ranked. They used, I believe that was, I think that there was a paper on the scientific collaborations, right? And what they tried to do is to predict, links in the scientific collaboration, which means who is going to write a paper with whom as a co-author. And they looked at the different, different features, right, that we described. And here is, feature importance, pretty much. And, surprisingly, this strange feature, which is 1 over logarithm of number of the nearest neighbors, comes as quite powerful, right? Then there is a Scott's score, different flavors of Scott's score. Then there is a page rank. Then there is a Jacquard coefficient. Then there is a similarity rank, etc. So pretty much all of them, do work. Some of them stronger, some of them weaker. This is just the same picture. It's just renormalized. But again, the point is, this one over the log works surprisingly well. Okay. Now, if I actually go and build a machine learning problem, well, yes, as we described, we have to evaluate, go through a lot of edges if we want to actually go through all of them. So it's good. It's better to have some idea of where in the graph you want to predict things, right? So you literally, like a machine learning framework, you throw in a pair and you just get back yes or no, right? You don't want to go through all the nodes, right? So you want to be able, for every pair, to just say, if it's going to be a link or not, versus ranking all of them and just taking top 10, right? So you want it to be, to be normalized the right way, right? And as we discussed already, highly imbalanced distribution, makes it challenging. This is yet another slide to just confirm what we discussed. This is again collaborations, and of course, researchers in academia do like to investigate those type of data, right? On collaborations, and it just says, for example, this is an actual collaboration, right? How much actual collaborations? This is millions of collaborations in the database, right? And how it grew from 95 to 2004, and that's all possible. And this is logarithmic scale, right? So 1,000 times more possible. So that's the class imbalance level. Okay, so what do we do? Well, as always, it's about feature generation, and we talked about them. Then we train, then we test. What we have not discussed yet is the fact that very often there is some content associated with links and nodes, right? And so if you put this in machine learning framework, you can easily incorporate that, right? And that's, for example, where this assortativity story can come in, because previously we talked only about the graph structure, and then it's assortativity in terms of node degrees. But we can also put a lot of features in there that just based on the nodes, right? On the values on the nodes. For example, we can put a gender. I don't know if it's true or not, right? But there's probably well, again, I don't know if it's true or not, but there is a feel that maybe within the same gender, links within social networks forms easier, right, than with opposite genders, or maybe other way around. I don't know. But the point is that the gender of two nodes can play a role, right? Age difference. Again, in social network, I would assume the smaller the age difference in between two nodes, the higher the probability that they're gonna connect. Geography. I mean, you name it, right? So there are a lot of content-based features that you can generate, and again, you just put it into this whole mix. Okay, so you have your network, you have your features, and then you do predictions. Now, this is quite interesting work where authors looked at discriminative abilities of features, right? So for a feature, I mean, again, if you build machine learning models, you want features that can discriminate two classes, right? So, what I mean is you have class A and class B, and then you have a certain feature. Well, you want this feature to take different values for each of the classes. If this feature takes the same value for both classes, it's useless, right? And the challenge usually becomes when the feature sometimes take different values for different classes, sometimes takes very similar values for different classes. Then this feature is weak. Then you look for other features, or you hope that when you have multiple features that somehow compensates, right? And so what they looked at different features, and they looked at two classes. For them, class is there is a connection between two nodes, and then there is another class, there is no connection between two nodes. And they looked, for example, at the typical graph distance, distribution of a graph distance. And by the way, this is connection, this is no connection, right? And for example, this is a feature of graph distance. And of course, when there is a connection, well, it's one step away, of course. And this is what you have for the graph distance. So this feature can be discriminating. These features, if you notice, I cannot see it's log of something. I cannot see it, but notice that there is an overlap, right, in features. And so whenever you take the feature is equal, for example, to this, somewhere here, well, it might tell you that it's from this class, or it might tell you that it's from that class. So this feature, but on this side, when the feature values are in here, right, then there's a much bigger chance that it belongs to the first class, because most likely with a small value, this feature, it's this class. So it's also useful. It's not as clearly discriminating as this one, but it's useful. This one is also well discriminating feature. So in fact, whenever you deal with machine learning problems, this is a very good exercise, right, to go and take the classes, in your training set, your features, and just see if they discriminate, right, if the distribution of the features in two classes is different. So what do you do in terms of setting up of machine learning problem? Well, you have your graph, right? And let's say for a second it's not dynamic graph, so it's not changing with time. This is a graph structure. What you do is you take, for example, pairs, right? Take a few pairs and hide those edges, right? And then calculate all the features without those edges, and then try to predict those edges, right? And if the real graph has it, when you predict that there is going to be an edge here, if you're right, then you just use your metrics, right, to calculate things. Now, that's pretty easy. It's becoming a little bit more challenging when you have time evolving networks, right? And that's usually most interesting when you have, your sort of network changes with time. You get more and more friends in Facebook, you get more and more collaborations. And the same way as in other machine learning problems, when you have this time dependency, you have to be careful how you set up training set and test set, right? Have you worked on on time-dependent problems in machine learning? Guys? Yeah, okay. So you're familiar with this a bit. So the idea is, of course, you're very careful in terms of, you need to take into account time when you do training. So you select, for example, let me just show here. You take, let's say, this part. What we have here, this is a time evolution, let's say, of the graph, right? And there is this different pieces of graph, how it evolves with time. You select particular time frame, let's say from this point to this point, and that's where you calculate your features. Then the next time frame is when you calculate your labels, and you think within that time frame if the new link has formed or not. So here is an example. We have two nodes, A and B, right? Let's say the feature was, two neighbors, and the feature existed. And yes, within this time frame, it formed an edge. So the label will be yes, right? At the same time, there is this node C and node D. They also existed. They have, let's say, one common neighbor. And let's say within this time interval, they did not form an edge. And so that's going to be a label no. Okay? And so then you actually go through all the graph and form those pairs, right? Those training set. Now, again, remember that the story is very much unbalanced. So most likely with negatives, so with labels n, you just downsample, which means you don't go through all the possible pairs. You can also, if the graphs are not large, you can actually do it on the entire graph or on a piece of graph. Now, if the graph is very large, you might even want to look in the different parts of the graph for training and testing exercise. Now, when you do testing, what you need to do is you train on this time frame, right? So this is your buffer for the training, and there you have sort of sub-buffer, first window for features, and then small window for labels. So this is your time buffer. Then you want to do testing, right, or prediction. You move it one step forward. Then you calculate all your features, right? And then you take and look at the labels. Of course, the key in this exercise that the testing labels should not overlap with training labels or with training anything. All right? And here is an example. And as I said, if a graph is small, you can actually work, as I described, carefully on this, on the graph itself. Or if graph is large, you can probably, deal with different pieces of graph for training and testing set. You wanted to ask something, right? Yeah.
You said about downsampling, like negative sampling, but is it okay to change the distribution between classes? Because when your model will be working, the distribution will be different, not downsampling.
Yeah.
So it might
overestimate, exactly. Exactly. So, and that's why I said, yes, you can downsample, but a little bit, right? So you should not change the distribution dramatically. It's better when you build this type of models is when you created your training set, right? And then when you train it, you actually change within the optimization function, right? Within the cost function. You change the weight of classes. So you assign higher weight to the class with a fewer examples, and lower weight in the class in the case. So you assign a higher weight in the case you made mistake with a low number of examples class, right? And less weight for the mistakes in the class with a lot of examples, right? That's what usually works better. But here you have, yes, I mean, you have to be careful, otherwise you're going to be skewed in your approach. So again, it feels like an easy problem in the sense of the setup, but when you actually start doing it, you realize that it is very, very easy to get, AUG 0.99, right? Which usually tells you that there is a problem. And typically the problem would be either with a sort of what's called, label leakage or signal leakage, when your training set is somehow gets a little bit of information from, test set gets information from training set, or you created this class imbalance. Now, since you know all this, of course the metrics are going to be precision recall, or true positive rates, false positive rates, ROC, AUC, the usual, absolutely usual stuff. Now, this, of course, there has been like lots of papers where people tried different methods on a different database. Databases, of course, as I mentioned before, for academicians, the best data available is about scientific collaborations, right? So all this, 2 different databases, a bunch of models, bunch of approaches, classification models. Well, you see the results. It's hard to comment. It seems like numbers are overall pretty good, but again, it very much depends on the data set, right? You're dealing with. And in some cases, I would assume with scientific collaboration, that's kind of strongly, a well predictable situation, right? You can actually see who can write papers with whom, because there is really strong communities in there. Again, since you're familiar with this, I don't need to spend a lot of time. Just to point out that yes, there are some methods that actually. And actually, this is, this is, but I cannot see which one was doing this. I think some of this is actually machine learning methods, right? And some of those just one of the features. And, this is a preferential attachment that was actually giving us the inverted AUG curve. But, for some particular data set, right? So there's different data sets. For other data set, the preferential attachment was giving us, a good curve. So that really meant here that the degree of the node degree, is not important feature in here, right? So they just ran it just with one feature, and it give you inverted things. Overall combination of all these different features, gives you pretty decent curve. All right, makes sense. I don't need to go through the details, right? What this is. Okay. By the way, since you all have seen this, who can actually explain to me what ROC AUG curves tell you?
How would your classifier in comparison with random guess? We can see if we draw a line from 0 to 1 1. It's how random guess works.
Uh-huh.
Above this random guess is better.
Okay.
It's below, it's worse.
And ROC. This is a curve, right? This is you select false positive, you get. Why is it a curve, right? So how do you? Why is it a curve? So how do you get to any of those points?
You choose a threshold. What is the threshold? Then you choose
right.
Which class to assign.
So yes, so you're mostly working with the ranking classifiers, right? And so for every instance, and here an instance is a pair of nodes, and the fact that it's going to be edge or not, right? It returns a certain rank. And so then, when you have all your nodes arranged by all the pairs arranged by this rank, you set up a threshold, and depending on the threshold, you're moving along any of those curves, right? And of course, you might increase true positives, but at the expense of increased false positives, right? And so in our case, what's true positive?
If it's really an H and we predicted
And false positive?
false positive, there was no H that we predicted.
Right, so there is no H, but we predict an H here, right? So what is rock auk? The area under the curve. Like, so what you just described to me is, the curve itself. What is the meaning of rock auk?
Square.
Oh, well, it's an area under the curve, but why is it? Do you know the actual meaning of it? Like in plain English or Russian? You actually started talking about it a few minutes ago. It is a probability, right, that randomly selected pair will be ranked above, right? The randomly selected pair out of the positive class will have a score higher than the randomly selected pair of the negative class, right? And so that's the meaning of the area under the curve. Actually, I don't think they write it here, but looking at this, probably like 0.7, right, or something. Okay. So then there's like many more models. We just talked, we just touched upon, very, very simple, sort of straightforward approach. There is, Markov models, Markov random fields. There is like probabilistic models, hierarchical models. So you name it. If you're interested, there's like huge literature on this topic. Plus, of course, all this can be connected to the story of embeddings, right? So you can think of this as, okay, let's take nodes, right? Nodes do not have any coordinates, right? They live in n-dimensional space where n is the number of nodes. Then you can actually run certain embeddings, right? Put it into low dimensional whatever subspace, and that embedding can be done through either, in the simplest ways, principal component analysis, but you can also, of course, use all the neural network approaches, right? All this deep learning story, TSNE or whatever, which actually projects your nodes on low dimensional space. And then you can actually use within that low dimensional space, you can, for example, use Euclidean distance as a metric, and then say, okay, if the nodes projected in that embedding next to each other, right, then they should have an edge in between those two nodes in the sort of original graph space. Okay? So that's another approach, and as far as understood, Andreevich talked about embeddings last time, right? Okay. So that's sort of another way to do it. There has been a lot of papers on this using embedding for link prediction within several last years. It's a matter of fashion, right? It's fashionable now to do those things. I would actually be careful and compare sort of more of the straightforward methods with those. Or, in fact, you can, take this embedding, take the distance between nodes as one of the features and add it to the mix, right? This is just a small subset of possible of papers on this topic. If you're interested, just Google, link prediction, and you will get hundreds of papers with very, very different approaches. All right. Any questions? Yes.
I have a question. Like you said that we have very unbalanced classes, like this bond overshoot network, but then we saw like local graphs to assess quality of our classifiers. Is it really right? Because it will show, like it will, Rockout will overestimate our quality of our classifier in case of imbalanced classes.
What's not good when you have imbalanced classes is to use accuracy scores. That's hurting you. But when you talk about like Rockout, and we can talk about this a little bit offline, in fact, because it's normalized metric, it's relative metric, right? So it's actually talking about true positive. I mean, these true positive or for this true positive, so it's relative metrics. So you really don't care here about the actual numbers, right? That's why you deal with this, but you don't want to use, where is it? you don't want to, that's why I'm saying this guy is very suspicious, because this one actually is heavy biased. I mean, if when you have like what you probably have in mind, when you have an unbalanced class, right? I can tell you, hey, there is no links appear at all, right? And according to according to the data set, well, I made like 3 mistakes, but so what, right? But that's why you don't do accuracy. But ROC-AUK is actually, because of the way it is calculated, it doesn't have this problem. And that's why actually people using it, I mean, well, most people don't think about it, but that's why they use it instead of accuracy. And accuracy, I usually don't look at it because it's just not true for unbalanced classes. Not good. Anything else? Okay, let's take a, 10-15 minutes break. So the second part today is really also about learning on graphs. We're gonna take a little bit different angle. We're gonna look at semi-supervised learning approach, and we'll look at random walks on graphs. One of the reasons is just wanted to show you sort of graph-specific methods, right? Because otherwise you can also formulate this problem in a similar fashion to the previous lecture. So, what's label propagation problem? Well, this is, it is what it sounds. You have some nodes on the graph that carry certain labels, and then some nodes on the graph where those labels are missing, and you would like to infer them, right? Or propagate the known labels to those unknown, to the nodes without those labels, right? In example, there are trivial examples. Give me an example.
For instance, in social network, we can have a community of people, and we can label them people with community. We want to find another people whom to recommend.
Yeah, we can do that. Yeah, that's possible. Or, even a simpler example. Let's say, I don't know, you don't publish your age in your Facebook profile. How can we infer that? How can we infer a person's age?
Look for age of his friends.
Exactly, right? And then maybe average. Or let's say somebody doesn't disclose his income, right? How do you find an income? Well, look for people similar to this person. You know how much they make. Well, that's what he makes. So, et cetera, et cetera. So there are a lot of ways, or geographic location, et cetera. Now, those approaches works only if there is one important condition is met, which is the values on the connected nodes are correlated, right? If they're not, then the fact that there is a connection doesn't mean anything, right? So, but for those sort of labels, features, those values that will be correlated for the connected nodes, that will work. This approach will work. Now, it can be applied directly to graphs. So when you do have graphs, you do have structure, you can just use it on the graphs. It is also a very powerful method, and actually originally it has been also used just for labeling of data points, right? Those that are not graphs. And to do that, the approach would be you take your traditional data points, right? And you can actually form a graph by, the similarity graph, right? A similarity network. So you go through all the points pairwise, right? Go through all the pairs, connect nodes and put a weight on the edge based on the similarity of those nodes. And if you think about, customer database, you'll create a similarity graph of the customers, or you can embed it into whatever dimensionality you want and use Euclidean distance, anything you want, but you can actually just impose this graph structure on top of your traditional data points. Okay? Now, why would I want to do this? So what sort of, what's extra powers are in there compared to traditional machine learning, right? Compared to traditional supervised learning. I mean, as we discussed previously, the major one of the major challenges in the supervised learning is you need to have labeled data sets, right? And so you have plenty of labels, then it's not a problem. It's challenging when you don't have a lot of labels. And so then you want to try to somehow compensate for not having those labels, right? And that's where some other ideas come into place. So we have supervised learning, right, where you have labels and you try to predict labels. Or you have unsupervised learning examples where you just try to detect patterns in the data, right? So find clusters. Can we combine those two ideas? You probably can, right? And that's what sort of semi-supervised learning is about, is the fact that you don't have a lot of labels, but what you try to do is you try to use similarity of the data points to improve your classification, which is, let's say you have a bunch of data points. You have some data points with labels, and then you have sort of other data points, but you realize that these data points are quite similar to those that already carry labels. So then you can easily spread labels on those data points that are very, very similar to those that are already labeled. And then you can actually run this as a supervised learning later on for either to confirm your selection or to do it for the data points where you really don't have anybody around it, right? And so you cannot easily propagate labels on those. So that's sort of the general setting of semi-supervised learning. Try to learn the structure of the data itself without labels, right? And then, add labels, and that will help you with small label data set. Again, in the sort of very simplistic fashion, if you think that your data points form a cluster, and you do know a few labels in that cluster, and those labels are consistent, you might actually spread them for the entire cluster. And then all of a sudden, you have lots of training examples with the right labels. Okay? So it just feels like a waste not using the structure of the data points of the data itself, the structure of the sort of the features, the structure of the feature set, right? If you don't have enough labels. So that's the overall approach to semi-supervised learning, and we're going to look at that approach here. That's sort of the overall overarching picture. There are some details, and we're going to actually connect this a little bit to random walks again to just show you one of the examples of how you can do it, but there are again many more ways of doing this. But conceptually, it's all the same. You look at the structure, and you try to use the structure to propagate labels, to spread labels from the nodes that you know the labels to those you don't know the labels, and that are structurally or in the case of graphs tightly connected to the known labels. Now, that would be a very easy problem if you had a sea of labeled data and just few unlabeled spots, right? Because then what we do, like you said, let's say if I want to infer somebody's age, I just look at the ages of this person's friends, right? Now, it's a little bit more challenging if half of the friends don't put their ages in their profile either, right? So then you cannot kind of confidently infer this person's age. So what do, right? Then you can actually start looking at the next nearest neighbors, the next nearest neighbors. But then the question is, okay, well, maybe there is third friend has certain age, but how does it age affects this particular guy's age? Maybe, through this sequence of friends, age can grow or age can decrease, right? Or maybe it's the same age, who knows? So that becomes a little bit more challenging, right? And that's sort of this whole problem is set up in the following way, that you do have some labels, right? Some nodes that are labeled, and here's some nodes that are labeled. And there's not that many of those, and the majority of nodes are unlabeled, and you do have graph structure. And so what you want to do is you want to guess, to infer the labels on those nodes. Okay? That's sort of the setup. Now, you can also think about this either as a classification problem, plus or minus, gender, whatever, or you can think about this as a regression problem. You want to assume, to predict, infer age or income or whatever you want to infer, if it's social, and if it's any other network, whatever you're trying to find. So as I mentioned, structure, knowing the structure, the connectivity pattern, can help only if the linked nodes, if the values are correlated, right? Because if the values on the linked nodes are not correlated at all, it doesn't matter. If I randomly assign values, there is no way the structure can help me. Now, as we talked in the previous lecture, networks do show a lot of assortative mixing, right? So it is bias or preference in terms of connections between nodes with similar characteristics. You have a homophily, you have influence when one person influences another person, or you have homophily, which is, if you have similar characteristics, you do connect, say, similar political preferences. People, tend to connect more often than with dissimilar preferences. And so in social networks, label propagation does work. There are some other networks where it will not work simply, because the connection doesn't really, the connected entities not necessarily have correlated values on them. So, what can we do? Well, the same ways as always with supervised learning. You have some nodes with given labels and some nodes with no labels, and then you try to set up a supervised learning problem, try to predict those values based on the features, right? And you can think about like local features, the features of the node, like node degree or anything else, and you can also think about link features. So how this particular node is connected to other nodes. So your feature can be a label on the neighboring node, right? And if there's a feature, then you can just easily set up a prediction problem. Now, you can actually build, very much a local classifier when you just use the features of your neighborhood. Or you can actually, have more of a collective classifier when you put as a features a lot of things that are not directly related to your neighbors, but towards other nodes. Like very simple, again, the simplest way to do this, and let's assume for a sec that we're actually just trying to calculate, either do regression or try and calculate the probability of the class. We can, for example, do some sort of voting, right? Like what I described, like what we discussed. You want to infer somebody's age. What do? Well, you just take neighbors, ages of the direct connections, and just say average them, right? Or maybe you can actually create like a weighted average depending on the strength of the connections. Or if you don't know age of one person, well, fine, you just skip that person. But the point is, you can try to calculate some sort of value, whatever value it is, and you can think about this as a probability, just going around its neighbors and picking up the labels of the neighbors. Now, there are a couple of challenges and a couple of problems with this approach, though it's very sort of intuitive, right? And especially if it's not probability, but say the actual sort of age value. The problem is if some of those missing, well, you don't know what to do with this. The other problem, of course, if you try to think probabilities, then it's not clear why do you actually adding them up, right? This is sort of strange idea to just add up probability of the neighbors. It just doesn't go well with all the probability theory. So what makes more sense if you do probabilities is, for example, to say that the probability of the particular node of whatever class it is does depend on the probability of the neighbors, and it is AND function, right? So the probability is sort of being, enhances by the neighbors, and if it is AND, it's a product of probabilities, right? It's a probability of this particular person belonging to the particular class. It is this times, the neighbor times the next neighbor, another. And then, of course, if you want to make it into a sort of nicer framework, you can also add the Bayesian approach, saying like, okay, yeah, but what is a priori probability of this particular class, and then work from there. Again, very simple. Trouble here is obvious. You don't know the probability on the neighboring node, or if it is 0, well, that's it. You're screwed, right? This whole thing becomes 0. So you have to be careful with this, but you can still do this by actually doing iterations and going through the entire network and just iteratively updating nodes, updating those weights until things converge. And it's possible. So, in a very simple example, and here I'm looking at the directed network. Yeah, here is the values. Let's say I try to infer it here on the first step. I infer it, and then I keep propagating, right? So, and then it goes to this one and this and this. So pretty much what it says, this approach, is you have to be kind of picky and careful where you start this process, right? You started from known nodes, and going from those known nodes, slowly change the neighborhood. So you don't start with the nodes you don't know, right? You just start from the locations you know and kind of spread this. If you can think about it as like waves going away from those nodes where you know labels, right? And sort of in a very sort of generic fashion, whatever function you use, the idea is, yes, you take the known nodes, the nodes with known labels, you form your local matrix, you either form your local classifier, or in the very simplest form, it's just not really a classifier. You, like we discussed on the previous slide, is very, very simple sort of formula, right? Which is, you can think about this as a bias classification problem, right? A bias classifier locally, or any other classifier, and you just keep iterating and spreading on every step, and just going through the whole network, and just keep repeating until everything more or less converges. And if you're careful with using sort of not the numbers, right, and missing values, it actually will work. Not that much math in here, not that many proofs, right? But empirically, it actually works. What I want to focus more a little bit on, actually pretty cool approach. Again, it has kind of a funny history. It was first, introduced as a little bit of ad hoc method, right? Or again, maybe I don't know. Maybe the authors knew the math behind it. But looking at their first papers, it was actually introduced as just an approach, and later on there was some math behind it shown. The same way, as what happened with PageRank, right, where it was just introduced as sort of a way to deal with, with this random, have this random surfer idea, and then it happened that, oh wait, it's a random walk, it's Markov chain, etc., etc. So here it's very, very similar. So the idea again, if we have labeled data, unlabeled data, and we would like to have some sort of consistent way to propagate labels across the entire graph. Okay. Here is the idea. Idea is actually kind of cool. Think that imagine that we try to simulate like a random walk. Okay, and we can start random walk at any node. Now, random walk. You can impose various properties on a random walk. For example, you can create nodes that absorb your random walk. So what does it mean? In general, random walk allows you to just sort of walk around the graph infinitely, right? And you're just visiting nodes, visiting. But you can also create sort of traps or absorbing nodes. And if the random walk gets to this node, it just stays on this node forever. You can think about this if you think about graph structure, and let's say there's directed edges. You can think about this absorbing node as a node that has an edge to itself, right? And nothing else leaves this node. So you get this node, you're stuck forever there, right? So it's absorbed. So the idea is the following. You start a random walk from an unlabeled node, right? So you're on the node that doesn't have a label. And you start randomly walking around. When you get, if you step and get to the node that is unlabeled, you just keep walking. But whenever you hit a node that has label, your random walk stops. You're absorbed on that node. And then the value, the label of that node, carries to the node you started from. Okay? Now, you launch multiple random walks from this node, and they will be absorbed at different nodes. And then the probability of your class comes up from the probabilities of the class of the nodes you being absorbed by. Okay?
If you hit the labeled node that we already listed, what we do?
So you start a walk. If you hit a node that labeled.
It had labeled and we visited it on the previous walk.
Oh no, it doesn't matter. I mean, every time we start a walk, and when we hit a labeled node, walk stops. We just sort of calculate that, okay, we counted it, then we forget this walk, and we start over. So if we get on the same node, that's fine, right, within the random walk approach. So that's the idea, right? Now, why is that way? Well, that's one of the methods, right, people thought of. But the reason is the following. The reason is, of course, you want to take into account, neighbors, right? You want to take into account next nearest neighbors, next nearest neighbors. You want to do it in some sort of consistent way, but you don't want to be biased, so you want to have some randomness introduced in there. And so it feels like this random walk story can give you, what you're looking for. And again, looking at the success of PageRank, that might be an interesting, might be a good approach. And in fact, this idea, it can be nicely formulated, and you can show that this approach actually converges. So it's globally converges, and it does allow you to consistently label all the nodes, right? And we'll talk a little bit about the math, not too deep, but you can go through the papers if you want to. So the idea again, this Pij is a probability, it's one-step probability transition matrix, right? Pij infinity, that really means the transition matrix after infinite number of steps, or until the absorption, right? It's not infinite, it's until the walk is absorbed. And the probability, it's called here y sub I, for the node to carry a particular label. C is really sums up from the probabilities of those walks, right? And the probability that P infinity is a probability starting from node I and ending at node J and being absorbed there, times the label there or probability of the label in there, okay? And so it's also very nice because it can deal both with, binary class or, if it's a probability, initial probability distribution of labels. So, the question is, how do we do this? I mean, obviously, for experimentation purposes, you can actually even write a simulator to do it, right? You can just literally launch random walks, do it multiple times, calculate those probabilities, estimate this, calculate this number, right? And do it from every unlabeled node. It's possible. Now, it's not very efficient, but just to verify the idea, you can do this. Now, with this approach, there's a very, very nice and clean mathematical theory how it can actually work through matrices and through Markov chains. And so the idea is the following, that we have to split all the nodes. I mean, we do have two types of nodes, right? The labeled nodes and unlabeled. So what we do is we renumber or reorder them such a way that from number 1 to number, I don't know, n, they're going to be unlabeled nodes, and then going to be labeled nodes. Let me actually see if I do it that way. Yes, at first it's going to be labeled nodes, and then unlabeled nodes. So then what happens is you can actually create this transition matrix, and it is one-step transition matrix from different types of node to different types of nodes. So remember, the nodes that are labeled, they are absorbing nodes. And that means you cannot go anywhere when you got on this node. There is no way out, so which means there is no transition out of this node. And you can only stay on this node. And so for this first part of the nodes that are labeled, the transition matrix is diagonal identity transition matrix. You got on the node, you stay on the node. Second part of the matrix corresponds to transitioning from labeled nodes to unlabeled nodes. It's impossible because, again, labeled nodes are absorbing nodes. So you get there is no way out. So it is all 0. Now, this matrix has the following meaning. Here, transitioning from unlabeled to labeled nodes, and that's possible. That's the random walk. And this is from unlabeled to unlabeled, which is also possible because you might have. So this is a direct transition from unlabeled to labeled. So it means there are some nodes that have labels can be neighbors to the nodes that do not have labels. And this one is from unlabeled nodes to unlabeled nodes. So, with the picture, it's possible that unlabeled node is connected to unlabeled node. And that's the matrix. And this is a one-step transition probability. So it is literally, normalized adjacency matrix, right? The same way as in PageRank, when we took the adjacency matrix and normalized by node degree, because you get to a node, right? And then if you describe a random walk, you need to decide which link you're going to follow, right? And if you go with equal probability, well, you just need to normalize by the node degree. Okay, so that's this matrix. And what we're trying to do is we're trying to see what's going to happen if you, and this is one-step matrix, right? So it is what happens, the probabilities that happens, when you make one step, one transition. Now, if you want to describe this very, very long random walk, what you do, and I believe we talked about it before, you take this matrix and if you want to describe n steps of the random walk on graph, you take this transition matrix and put it into the nth power, right? Does it make sense? So one-step transition matrix is P. If you want to describe what happens with your system in 2 steps of random walk, it is P squared. It is you do one step, then you do the next step, right? In 3 steps, it's 1 step, 2nd step, 3rd step, it's P cubed. In n steps, it's P to the power of n. So if you actually do this, or I'll put here P to the power of t, and you take t to infinity, what actually happens is, this stays I, this stays 0. This submatrix, and trust me on this, when you multiply by itself many, many times, it becomes 0. And here, for this combination, we can show that it converges to this value. Well, the reason for that is this one is very much, I think we talked about this at a seminar sometime. It's like 1 divided by 1 minus x, and you have then you can represent it as a sum of powers, right? So if you take 1 divided by 1 minus x, right, it's sum of x to the power of n. So that's but you can do the same kind of things with matrices. This is a matrix inverse, which is pretty much 1 divided by I minus p, right? And that's how you can actually represent it. But the point is, whenever you have this, it becomes a very coincidence formula. So the reason I'm going into all this is because if we remember what we were trying to do, we're trying to say, okay, what's the final state, what's the initial state, and how they're connected. So this tells us the probabilities on labeled and unlabeled nodes after the walk. This matrix describes walks. This is initial probabilities on those nodes. That's how it works, right? You have a distribution of the probabilities on the nodes, you multiply by the transition matrix. That's the distribution of the probabilities of the nodes you get after the first step, right? You do it, multiply again, it's after the second step, etc., etc. So what you see from this equation instantly, that this stays the same, which is good, right? We don't change labeled nodes. Whatever labels were there, they remain the same. But for those that are unlabeled, they actually, now we can compute their values. And that's what the values would be. So labeled stays the same, unlabeled being computed through labeled nodes. And there is these two matrices here, one-step transition probability matrices. This is from unlabeled node to unlabeled. This is from unlabeled to labeled. And in fact, if now for this to work, this inverse should exist. And one can show that it always exists. It's non-singular, is what they call, the authors called it labeled connected graph. But the point is, you can always, from unlabeled node, you can always reach labeled node. Eventually. Not directly, you walk around, eventually you end up at the labeled node. So if you can do this, then this matrix will be non-singular and the inverse exists, and you can just calculate this. All right. I know that was a sort of long story. The point is there is a very, very simple algorithm that you can actually implement. And the algorithm is the following. You have your graph. Okay? The graph has some labeled nodes and some unlabeled nodes. You initialize your system, you initialize your equations with labeled nodes that are known. You take your graph and adjacency matrix and you calculate probability transition matrix, which is your adjacency matrix normalized by the out degrees of your graph. Which is, again, this is the adjacency matrix. Here what you need to do is you just divide by node degree. That gives a probability of transition. The same thing as we did with page rank. And then you literally have to just repeat these very simple iterations. The new values is equal all values times this, right? I mean, all values times this times the matrix. You get the new values. And just keep repeating. At the same time, you do reset those that are all unlabeled nodes. And these iterations will converge to the solution and the solution we just described. So, extremely simple algorithm, guaranteed to converge. And that's how, and also internally, it does take care of those nodes that are not directly connected, that directly do not have labels. Okay? Make sense? Even if you don't understand completely this story, the approach should make sense, does it? No? Sort of? Kind of? Okay. Again, so what we're doing is we're trying to simulate random walk, right? So what we're saying is the nodes that have labels, they're absorbing nodes, and our random walk will end on those nodes. And what we're trying to do is we're trying to predict the labels of unlabeled nodes through the labels of the node where your random walk end, right? We're just saying, okay, if it ends on this label, that label should be carried to your unlabeled node. And if random walk goes through multiple, we end up on the nodes with different labels, well, your label of this unlabeled node becomes a combination of those labels. So that's sort of what happens there. Now, the way we describe this is through transition probability matrices, and with an algorithm, you can actually don't really need to simulate this. You can end up just multiplying matrices, and that will give you that result. Better? Still kind of not clear? All right. Okay, after you do it in your homework, it will be crystal clear. Okay. Now, there was, in fact, that paper started, the flood of different papers on a similar topics, where, there is, if you look at the algorithms, they're very, very similar. There's slight differences the way, you compute those transition matrices. Here, you can actually, instead of just having transition matrix itself, Here there is, transition matrix, plus you add a little bit of initial state. So there is like lots of different flavors of how you can do this, right? And depending on that, you might get sort of better results, worse results. It also depends on things. Hey guys, at the back of the class, gentlemen, ladies and gentlemen at the back of the class. Алло, народ, я к вам обращаюсь. А вы вообще, простите, куда пришли? А чего вы ждете? А что вы здесь ждете? Если вы ждете, сидите молча и ждите, ладно? All right. So that's the approach. Now, there are other ways of doing this. One of the ways is also through what's called regressional graphs. That's something you might probably think of, especially if you did a lot of engineering. That's something kind of naturally comes into mind. Imagine that you try to do regression, right? And let's say you have physical mesh, right, network. And let's say your nodes carry or has a meaning of a temperature, right? And let's say you're trying to solve the problem. Here is a plate, and that metal sheet, and you have temperature in the different parts of that, right? And you measure it at certain locations, but you cannot measure it everywhere. And you're trying to predict what the values would be at those points where you cannot measure it, right? So how would you predict those values? Yeah, you can approximate through nearest neighbors, if those nearest neighbors have certain values. But you make a very important assumption about this whole, about the entire function. That's probably your temperature distribution is quite smooth, right? And it's a metal, very good thermal conductivity, so probably distribution is quite smooth. So you can think of, okay, you know what? There is some sort of smooth function, right, that I can imagine on top of my metal, and I can try to literally interpolate that function. I can sort of anchor it to values that I know, and I'll make sure it is smooth. It's I can take some polynomial, and then for the unknown locations, I can just take the values from that polynomial and assign it to unknown location. Right? Make sense? Okay. So the key there is that the function has to be smooth. Then, it carries information about neighbors and next nearest neighbors, etc., etc. So if you think about this in terms of mesh, now, switch from mesh to a graph where it's not necessarily sort of direct connections, forget about temperature, think about overall properties on the graph, but the idea is the same. What you're trying to do is you're trying to interpolate across the graph, and every node, you have to select the interpolation function. And the same way as, again, in regression, in machine learning, you can take, linear regression, you can take, whatever. You can actually do regression trees. You can do, random forest with regression. I mean, any functions you want, right? That is a regressor. But on top of it, you can also put some sort of extra constraints. And the extra constraints, you want this function to either match go exactly through the values that are known, or don't be too far away from those unknown. And you don't want this function to kind of oscillate or change a lot. You want it to be smooth. In machine learning, we call it, what do we call it in machine learning? This force, when we force a function to be smooth. Regularization, right? So we introduce certain regularization, preventing function from oscillation, right? And so that's pretty much what you can do. You can start, and you can have initial labels. You want to make sure that the function that you're trying to learn, quite close to the labels on the nodes where we know labels. You want it to be consistent with the structure, which means labels on the nearest neighbors. You don't want to be very different, right? And that's what forces those things to be close to each other. And you're also looking at, if needed, some additional regularization that prevents the function that you're learning to kind of, grow dramatically, right? Or if you want to prevent it from oscillating, you'll probably put here like gradient, right, or derivative that will force it to be smooth. And this will force it not to grow too much, right? So then you can, for example, take all this, for example, three formulas, right, 3 equations. Each of them has a very particular meaning, and add them up, right, in the functional. And then you can optimize this and find the solution. You can find function y that close to known values on the nodes that have values, that provides us consistent values on the nearest neighbors, on the nearest nodes, and that doesn't grow too much and maybe not oscillating too much. Okay? And then you just combine those 3, and then you solve it and find this functional. Make sense? Okay. And there is like entire zoo of different methods. I don't expect you to go through all the formulas, but this is just for you to understand. There is one method which is proposed in 2002 that was just using the very first thing, just having consistent labeling. Then there is another method proposed a little bit later that uses consistent labeling plus being close to the values on the nodes, and you name it. There's like a bunch of those different approaches, but again, they all carry the same idea. You create this functional, and then you try to find a function that satisfies all these conditions, and you do it through optimization. And there are a bunch of names that being used for those type of approaches. One of them is like for example, it's called Laplacian regularization. So in order to solve this problem, in order to find this optimized solution, and you can write it in terms of matrices here, you can actually use eigenvalues and eigenvectors of the matrix, and then you look for a basis in terms of this eigenvalues and eigenvectors. And it's called Laplacian regularization because when you write this difference, it becomes a Laplacian matrix, and we talked about Laplacian matrix, I think, on one of the lectures when we talked about community detection or graph partitioning. So, but the point here is, again, you write some sort of functional form, and then you try to find a function that optimizes this. And you can use it. You can use a regression if you want to, or if you want to be very smart, again, you can use like any other functional form you want, right? And that sort of overall approach. Okay. So I don't want to go into a lot of details here, but again, the story is very simple. You compute degrees, you create this Laplacian matrix, which is degree matrix minus your adjacency matrix. Then you compute smallest eigenvalues and eigenvectors of the Laplacian matrix, and then with respect to this basis, you find the optimal combination of of eigenvectors that reproduces your functional, and that gives you the result. So let me jump to here and just sort of sum up. There are various ways you can propagate labels on graph, right? We talked about like nearest neighbors, which is like the most brute force. You look at the nearest neighbors and you use the values to assign to the node where you don't know the label. And that can be either class label or it can be the regression value. The other way is to, for example, use a random walks approach where you start walking from one node and end up to another and some other nodes, and then you calculate this probability distribution over the graph. Or there is an approach, as we described, as I described the last one, where you just sort of forget about all these local methods and you just think about this globally in the sense of, hey, I have this data and I want to map a function to this data, but additionally to typical constraints, like what you usually do in machine learning, if you have the usual constraint, if you want to solve a machine learning problem of regression and you have data points, what you do, you just select a particular class of function, right, to map to those points. Now, you don't want, for example, your function to maybe go through all the points, because then it's going to be overfitted, right? You introduce regularization. You can use, either you can use trees or you can use regression, linear regression, to map those points. Now, the only difference, what's being added here to that approach, is you're not just using simple regression, but you also add this notion of the neighboring points, data points. And you just want to make sure that those points that are geographically next to each other, and geographically means they're connected by your graph, they carry similar values. Right? But other than that, it's exactly the same approach as what you would do with just usual regression on a data set. Okay? So in this sense, this last approach is the most sort of generic. You can pretty much use all the machinery that you learn in machine learning. While the first two, they're much more sort of graph specific because you're actually walking on the graph. All right? Okay. So you look very sad, sorry. Okay, so here is the examples. Here I implemented this label propagation example. This was a graph, and again, for this type of problems to be challenging, look how many unlabeled nodes and how many labeled nodes we have, right? If it is sort of other way around, if we have a lot of blues and a lot of reds, then it's no-brainer to color those that are not colored by the nearest neighbors, right? The challenge here is that you do have, first of all, few blues and few reds, which means you just have a few labels. And second is that sometimes, well, they're actually connected, right? And so that kind of makes your prediction a little bit more challenging. So let's see how this method actually works here. That's sort of the coloring that it creates, right? And for those, if you notice, is those that are sort of behind those red nodes, they're all colored red, right? Those that are behind the blue nodes, they're all colored blue. And then in between the red and the blue zone, there is sort of different colors, right? And it's color-coded, of course, according to, let's say I assigned the red to be 1, the blue being -1, and everything else is sort of interpolated between them. Okay? Make sense what it does? All right. Now, and I don't have another example? Too bad. Wait. Here is this. Here is a different example. So here is a different example. Notice what I've done here. I kind of put the red node in here, then the blue nodes, and another blue node, and red nodes to a little bit confuse the algorithm, right? So it's becoming not so obvious. And just see how it behaves. And it's still kind of interestingly enough, colored this corner in blue, but the rest, due to, I think, these red guys, it kind of spread around and became red. Okay? So it is sensitive, of course, to positioning of your red and blue nodes, and so it more or less works. Okay, so that's it with that topic. And here's a bunch of references. Again, this is a sort of very popular and quite practical topic within overall graph learning. And if you're interested, go ahead. There has been a lot of activities in there. But the bottom line, the summary of those two examples of the two lectures is that you have machine learning methods, and you can use them within graphs and networks, And the challenge there is important there that you do have connections, and so you need to be careful how you build your train and test set if you just wanted to map it onto the machine learning methods, right? And the other challenge is typically when you use machine learning, your samples, right, your data points, the one you train on, they are independent, right? They come from the distribution and they're independent. Here, very often, they come from the graph, and so they're connected and they're correlated. And that makes it more challenging to actually set up the right training schema. Plus, as we discussed at the very beginning, you quite often have the situation when the label space is sort of becoming overlapping with actually feature space, in the sense that you're trying to predict existence or non-existence of edge, but when you calculate features, you use edges to for example, calculate the node degree. So you have to be very careful in terms of what and when you're using to avoid signal leakage, right? But other than that, this is pretty much where your machine learning intersects with the network science. Okay? All right, and I hope on the seminars and labs you will actually have some chance to experiment with those methods and actually predict some useful things. Yes?
Question about the last examples. At the end we have some unlabeled nodes, so shouldn't we label them randomly as red or blue, or we just let them to be labeled, or they are just another class?
What do you mean unlabeled nodes? Which one?
Node 9, 10.
Oh, okay. No. Okay, sorry, I apologize. No, they also labeled. It's just the neutral color here was this yellowish. And so what happened is, notice I could have done this problem as a classification problem, right? And just label them red and blue. Instead, I said, okay, let's make it as a probabilistic problem, and let's make it such a way that there is a certain probability that's going to be red or blue, right? And then just color code, according to it. And so those that are dark, this means this probability of them being red is very high, right? And those probability of them being blue is also very high. And for these guys, they're like 50-50, right? And so and so the color here is not the original color. It's not like, we don't know anything about them. We know, but it just means the chance they have equal chances of being, or very similar chances, and that's just sort of color mapping. Okay? So you do, you do of course get the value for every single node. And it's just for you like setting up at the threshold what you call what. You can just binary color it. Anything else? All right, then we're done for today. Thank you.